TypeScript's whole promise is catching mistakes before your code ever runs, and level 1 is where that promise gets real. We're covering 5 lessons today, in order: setup, basic types, control flow, functions, and interfaces, the exact toolkit you need before writing anything bigger. First, get TypeScript running on your machine. We'll install it, write one real program, watch the compiler catch an actual type error, and set up the project config real codebase's use. You install TypeScript itself as an npm package, almost always as a per-project dev dependency rather than a global tool. Once it's in your project, run the compiler through npx so you're always using the exact version your project expects. Here's the whole idea in one tiny function. Greet takes a string parameter and returns a string. Nothing exotic yet, just enough to see TypeScript syntax for the first time. Compile it with TSC, then run the plain JavaScript it produces with Node. TSC type checks your code and then erases every type annotation. Types exist only at compile time and cost nothing once the program is running. Now pass a number into that same function instead of a string. TSC refuses to compile at all. It names the exact argument that's wrong and why, before the mistake ever reaches production. Real projects don't call TSC against one file name, they use its config.json describing the whole project, which JavaScript version to target, where source and compiled output live, and crucially, strict mode turned on. For quick iteration, tsnode skips the compile then run cycle entirely. It compiles and runs TypeScript directly in one command. It's slower for production use, but it's the friction-free way to work through exercises like this one. With your environment ready and a working compile-run loop, the next question is what types are actually available to you day to day. That's exactly where basic types come in. TypeScript gives you a small, precise set of primitive types, plus 2 ways to handle values whose shape you don't fully know yet. Let's go through the ones you'll use constantly. String, number, and Boolean cover most everyday values, and notice there's just one number type in TypeScript, no separate int or float. TypeScript also infers types automatically from whatever you assign, even without writing an annotation. Arrays use square brackets, like a number array. Tuples go further. They're a fixed-length array where each position has its own known type, which is perfect for something like a paired status code and message. Any switches off type checking completely. It'll even let you call a number like a function and only blow up at runtime. Unknown is the safer alternative. It also accepts anything, but forces you to check the actual type before you're allowed to use it. With strict mode on, null and undefined aren't silently allowed everywhere. You have to opt in explicitly with a union type, like string or null. That one setting alone prevents a huge class of cannot read property of undefined crashes. One more small type worth knowing, void, for functions that don't return anything meaningful, like a logging helper. There's no return statement here at all, and TypeScript is perfectly fine with that. Once you know the shapes your values can take, the natural next step is branching and looping around them, and TypeScript adds something extra to that. It actually narrows those types for you. If, switch, and loops work just like JavaScript, but TypeScript layers real type narrowing on top, so the compiler tracks exactly what a value can be inside each branch. Inside the typeof ID equals number check, TypeScript already knows ID is a number for that whole block, and a string in the else. This is control flow analysis, and it's why you end up writing far fewer manual typecasts. A switch over a string literal union like direction north, south, east, west lets TypeScript verify every case is actually handled, which catches typos and missing branches at compile time instead of at runtime. Truthiness checks are convenient but a little blunt. They treat zero and empty string as falsy too, which isn't always what you want. When 0 is a valid value, check explicitly for not equal to null instead. Loops work the way you'd expect from JavaScript. For iterates values, which is most common for arrays, for iterates keys, mostly for objects, and while and do-while loop on a condition rather than a fixed count. The never type represents something that literally can't happen. Pairing it with an assert unreachable default case in a switch means if someone adds a new shape variant later and forgets to handle it, the compiler errors immediately. You've now got safe branching down. But none of this matters much until you're writing it inside functions with real parameters and return types, which is exactly the next lesson. Functions are where types earn their keep the most. Let's cover parameter types, optional and default parameters, REST parameters, and typing a function as a value you can pass around. A basic function like add takes two numbers and returns a number. TypeScript usually infers the return type on its own, but annotating it explicitly is good practice for anything other code will depend on. An optional parameter, marked with a question mark, may be left out entirely. Its type automatically includes undefined. A default parameter goes one step further, supplying a fallback value so you don't need a manual undefined check at all. REST parameters, written with 3 dots, collect any number of trailing arguments into one typed array, so some can take 2 numbers or 20, and every one of them is checked as a number. A function's type, its parameter and returned shape can be written down and reused on its own, which is exactly how you type a callback parameter, like the operation passed into apply operation here. When a function's behavior genuinely changes shape depending on how many arguments you pass, function overloads let you declare each valid call pattern separately, then write one implementation underneath that handles all of them safely. With typed functions in place, the last piece is describing the shape of the objects those functions actually pass around, which is what interfaces and type aliases give you. Last lesson, how to name the shape of an object so it can be reused everywhere through interfaces, type aliases, and TypeScript's distinctive structural typing. An interface like username's a required shape ID, name, email. Any object assigned to a user-typed variable must have exactly those properties, or the compiler rejects it immediately. Properties can be marked optional with a question mark, meaning they may be left out entirely, or read-only, meaning they can be set once at creation and never reassigned again. A type alias can name any type at all, not just object shapes, a union like status here, or a simple alias like user ID for a plain number. For everyday object shapes, interfaces, and type aliases are nearly interchangeable. This is structural typing. TypeScript compares shapes, not names. This plain dog object was never declared as named, but it has a name property of type string, and that alone is enough to satisfy the interface. Interfaces can also extend one another. Circle extends shape here, inheriting its color property while adding its own radius. It's a clean way to build up related shapes without repeating fields across every interface. That's the full Level 1 foundation setup: types, control flow, functions, and now shapes. Everything in Level 2 builds directly on these 5 lessons. If you want to practice any of this yourself, every lesson from today is linked below in the order we covered them: setup, basic types, control flow, functions, and interfaces.